So I want to talk more about just methods of integration today to make sure we're all kind of have good ideas about how to approach problems. So today's the 13th. So methods of integration. A few things let's just make a quick list of the methods we have available to us. And I would say the first thing you have available to you is, can you simplify it? So simplify. For example, something like the integral of x cubed plus 2 times 2x plus 3. That's something you could just multiply out and then integrate each term. Or something like x cubed plus 5x squared over x. That's something where you can divide each term by the denominator and then just integrate each term. So if you can simplify, great, you should. But sometimes you can't. And so then we try other things like a u substitution or integration by parts or partial fractions. And for the most, I should list one more thing. And then kind of at the bottom of the list, we also have a U sub with a back substitution. And that's kind of the full list as far as unless I'm forgetting anything. I don't think I'm forgetting anything. That's pretty much all we've got with these methods of integration. And I've kind of written them in the order I would imagine trying them. If it doesn't just simplify, I'm going to try a U sub first, or at least think about a U sub first. And if not a U sub, probably integration by parts. If neither of those things, partial fractions. And hopefully you can recognize the difference between what's going to look more like integration by parts and what's going to look more like partial fractions. Partial fractions problems have kind of a very specific look, right? Partial fractions, you have to have a rational function. And the bottom better factor. Whereas for integration by parts, that's where we have what we like to call a mixture, right? You have like an e to the x and a cosine of x, or a natural log and x to a power, right? You have some combination of usually logs, algebraic terms, or as I will often say, any power of your variable, trig functions, and exponential functions. So let's look at some examples. I have a few examples in my mind here. So let's say we have something like, we're gonna compare two integrals here. We're gonna look at the integral of, sure, x times e to the x squared dx versus the integral of x times e to the x. And while these look pretty similar, they're in fact very different in that they require totally different methods of integration. So I'll point out neither of these simplify nicely, right? Or I should really say both of these are as simple as they get, right? You cannot simplify these further. So we definitely can't simplify them. I would first look at either of these trying to use a U substitution. So looking at this first one here, I'm going to try letting U equal x squared. And if I do that, I'm happy about it because my derivative, my du dx is equal to 2x, or as we would usually write, our du is equal to 2x times dx. So then, seeing that I have x times dx in my integral, that means I'm going to move forward with this u substitution, right? I have the thing essentially that I'm looking for. I'm just going to correct this by multiplying both sides by 1/2 and saying 1/2 times du equals x times dx. I'm going to say this every time practically. Whenever you're doing u substitution, you want to make sure that the dx du transformation happens first. So whatever pieces need to get grabbed up to turn into du, you have to take those. So this part and this part are both going to get replaced by just 1/2 du. So if you want to do something kind of weird, take an intermediate step here. My intermediate step, I could say this integral is equal to the integral of e to the x squared times 1/2 du. I probably wouldn't usually write that, but I just want to show you that we're just replacing the x dx with exactly what it's equal to. Everything else, e to the x squared, staying just as is. And now we're going to continue translating it to u and be like, oh yeah, my x squared, that is exactly what u is equal to. So I'm going to rewrite this as the integral of e to the u times 1/2 du, but I'm going to write the 1/2 constant multiple out in front because we do. Because it's convenient. You don't have to, though. If you want to leave that 1/2 inside, totally fine. This one always feels kind of anticlimactic because when we anti-differentiate e to the u, we just get e to the u. So we get 1/2 times e to the u plus c. And then we plug back in because we started with an indefinite integral, meaning our answer better be a function and it better have the same variable that we started with. So we have to end with x's if we started with x's. We get 1/2 times e to the x squared plus c. And if you were to take the derivative of this, the chain rule would make you multiply by the derivative of x squared, which is 2x, which is what's giving us this x here. That's also kind of how you're thinking about what you want to pick for u, right? The u is the thing you are going to end up taking the derivative of in your chain rule. The derivative of e to the x squared is e to the x squared times 2x. And the 1/2 and 2 cancel out to give you just an x. On the other hand, this other problem is not a u substitution. There's not a good choice for u here. I mean, I can start going down the list. You could let u equal, you should never let u equal x in a u substitution. Because if you do, your du is just dx, and you're literally just rewriting the exact same integral with a different letter. So never a good call to let u equal x for a u substitution. Totally fine for integration by parts. We could try, I'm really just pretending here, right? We know this is not right. U equals e to the x, du is e to the x dx. That's a problem as well, because if I take care of my e to the x dx, I have an x left over, and that just seems like not the right way to go. You could do it this way really, really difficultly. If you really want, you shouldn't do it this way. This is definitely, and I should back up here. Here's what I see. I see a mixture in both of these problems. I see x to a power and an e to the something. I see x to a power and an e to the something. In one of these mixtures, we're doing a u sub. In the other mixture problem, we're doing integration by parts. And that's pretty typical. If you have a mixture of more than one type of function, it's usually going to be a u sub or an integration by parts. If it looks more like a function inside a function, probably more likely to be a u sub. But if it doesn't, if they look kind of more just generically not that different than usual, more likely to be integration by parts. So you're going to integration by parts. And we're going to talk more about integration by parts here because someone asked me a good question and I want to kind of explain here. So let's talk more about integration by parts. The usual setup is we're writing that the integral of u times dv is equal to u times v minus the integral of v times du. And I think either somewhere in someone's notes or in the textbook, they do something like this. They say u is equal to f of x, and you don't need to write this down, by the way, if you do not want to. And v is equal to g of x. And your du is essentially f prime of x dx, and your dv is g prime of x dx. And I got a question from someone asking me, like, why we picked, essentially, why didn't we pick u and v instead of picking u and dv? And the reason is because we're starting with the left-hand side of this formula. Our job is to look at this integral that we're given, identify the pieces that are going to make it then turn into something that is easier to deal with. So we're going to pick, in this problem, we are going to pick u equal to x. And we're going to pick our dv equal to whatever's left in the integral. So my u is x, and the leftovers are all of e to the x times dx. So we're picking dv equal e to the x times dx. Or in this notation, we're picking what g prime is already equal to. So we're not starting with g and finding g prime. We're starting with g prime and finding g. Or we're starting with dv and finding v. So these are the pieces we always start with when we're thinking about using integration by parts. That's the left side integral, right? If you look at, right, if I plugged in u and dv, I have exactly the integral of x times e to the x dx, which is the integral that we're starting with. But we don't know how to integrate that, so we're going to use this process to rewrite it in an easier way. So we have to fill in the rest of the other pieces here. Our du is equal to 1 times dx, and our v, which is the antiderivative of e to the x, is also e to the x. And then we're going to fill in the other side of this formula. So we're going to say that our integral, the integral of x e to the x dx, is equal to the u times the v that we found. So the u times the v is x times e to the x, minus the integral of v times du, which is our integral of e to the x times dx. And the whole point is that this new integral should be easier to deal with. Sometimes that might mean doing integration by parts again, but sometimes that might mean it's something you now know how to integrate after maybe simplifying it. Here, we know how to anti-differentiate that. It's just going to give us minus the integral of e to the x is also e to the x. And that's our answer there. The nice thing about integration, or one nice thing about integration by parts that I like is that you're not actually using u and v, like you're not changing things to u's and v's, you're just kind of naming things u and v, but then still writing whatever variable you're originally using. So it feels less terrible to me in that way. Let's look at some more examples. Let's say, yeah, we should do some of those. I feel like we didn't spend enough time with integration by parts, so we should do more examples of integration by parts. Let's look at something like the integral of x squared times cosine of 3x. So definitely not a u substitution. There's no good choice for you, or the only plausible choice for you is 3x. You're really not changing anything if you let u equal 3x, because you're still going to have some variable squared times cosine of your variable. This is definitely an integration by parts problem. So what's a good choice for you here? Well, let's see. I know I briefly mentioned it, but this acronym again is LATE, L-A-T-E, for what we pick u to be in an integration by parts problem. So first we pick u to be a logarithm. I don't have one. Then we pick u to be, again, people say different things here. I like to say any power of my variable or of x. And here I can definitely pick that to be x squared. But if I didn't have that, I'd let u be a trig function, and I would almost never let u be e to the x. So here we're going to let u equal x squared, and our dv, which is just everything left, has to be all of that. It's cosine of 3x dx. Our du is the derivative of x squared, which is 2x, and then we multiply by dx. And our v is the antiderivative of cosine of 3x. And this is where you would actually maybe need to use a u substitution. But we're not going to, because we know it's a short enough process here. So we know that the antiderivative of cosine of x is just good old sine of x. So the antiderivative of cosine of 3x should be sine of 3x divided by 3. So that's our v. It's 1/3 sine of 3x. And now we're going to toss this all into the formula. What formula? The ultraviolet super voodoo formula, of course, right? uv minus the integral of v du. That's going to be u times v, so x squared times 1/3 times sine of 3x, minus the integral of v times du, which is, sorry, I pointed at the wrong thing, because usually I write these in the opposite order. V times du, which is 1/3 sine of 3x times 2x dx. Here's where you have a choice, and I typically prefer here to pull out any constant multiples. So I would like to rewrite this as 1/3 times x squared sine of 3x minus 2 times 1/3 is 2/3 integral of x times sine of 3x. And the bad news is we're still in a situation where we have to use integration by parts, because I don't know how to integrate x to the first times sine of 3x. So we're going to let u equal. Now here's a good thing to know. If you're doing integration by parts repeatedly, you should always be making the same type of choice for u and dv. So in the first integration by parts, if I let u equal x to a power and dv be a trig function, I better be making the same type of choice here. U still better be x to a power, dv still better be a trig function. And that's all. I'm trying to think of, like, if there's any time where that's not true. I'm pretty sure that's always true. If you're doing repeated integration by parts, you have to be making the same type of choice in each step. So here we're going to let u equal x, which is a totally fine choice for integration by parts. And dv is going to be the rest, which is sine of 3x dx. Our du is 1 times dx. And our v is the antiderivative of sine of 3x is negative cosine of 3x divided by 3. So so I should point out this whole uv minus the integral of v du thing, that's all going to is going to replace what's inside this integral right here. So it's all going to get multiplied by this negative 2/3 out in front of it. So in the next step here, we're going to still get our 1/3 x squared sine of 3x minus 2/3 times our uv minus the integral of v du all multiplied by this negative 2/3 here. So it's going to be uv, so x times negative cosine of 3x over 3 minus the integral of v times du, which is negative cosine of 3x over 3 dx. The rest of it is not too bad. It's going to be integrating something we know, and maybe, well, again, I probably wouldn't try to simplify too much, especially on an exam here. If I was simplifying this a little bit, I'd have 1/3 x squared times sine of 3x. I can distribute this negative 2/3 to this first term here and get a positive 2/9 times x times cosine of 3x. It's positive because it's a negative 2/3 times a negative cosine. And then minus times a minus times a minus is minus 2/9. And I'm going to write the integral of cosine of 3x, even though I know we could do that. And then to finish the problem off, be the same stuff here. Sure, we can write it one more time, even though it feels terrible. See, 1/3 x cubed times 3x. X cubed? Don't be careful, right? It's really easy for a 2 to accidentally turn into a 3 if you're not looking that closely. And then 2/9 x times cosine of 3x. And finally, minus 2/9 times the antiderivative of cosine of 3x is sine of 3x over 3. Plus c. So we're just chipping away at this integral, and every time we do an integration by parts, we make that integral a little bit easier to tackle until eventually it's easy enough that we can actually find its antiderivative. Is that a question? Of course, you can just say, "Hey James, we can't see everything," and I will happily move things around. And I really should move a little bit left here because there's this little thing that's always like right in the way. Okay. There, a little bit better there. Cool. Let's see, I have other things. Oh, I should pass around the attendance form before I forget about it. Yeah, let's look at couple more things. So sure, yes. Paper. So let's look at a couple more, actually one more kind of comparison here. Like the integral of, yeah, sure. X cubed natural log of x dx versus the integral of natural log of x cubed over x dx. Okay. Which one, the one on the right or the one on the left, which one looks like it's more likely to be a U substitution? This left one or this right one? Sure.
Well, right.
Right. That's what I'm thinking too. I see a function inside the function here. I see this natural log of x getting cubed. And also importantly, if we make that our choice for u, its derivative is there, right? If we let u equal the natural log of x, our du is 1 over x times dx, and we have a 1 over x times dx. If it helps, it's certainly totally fine to rewrite this integral as the integral of the natural log of x cubed multiplied by 1 over x dx. So it's really easy to see that we have the integral of, well, our 1 over x dx is just our du, and the natural log of x cubed ends up being just our u cubed. So this ends up being u to the 4th divided by 4 plus c. That is a u, not a 4 right there. And then that's going to be the natural log of x to the 4th divided by 4 plus c. On the other side here, not so much, right? There isn't a good choice for u. because neither of those things, if we choose them, their derivative isn't really there. If you choose u equal to natural log of x, its derivative is 1 over x. We don't have that. If you choose u equal to x cubed, our derivative is 3x squared. We don't really have that. Also, as observed over there, we don't really have a function within a function, which is also kind of a hallmark that means we need a u sub. So here, this is definitely integration by parts. We're going to pick u equal to what? You have one of two choices. It's either x cubed or natural log of x. Who votes for natural log of x? Who votes for x cubed? And the answer is, well, if we look back at the acronym, we should pick u equal to a logarithm if we've got one. So we should pick u equal to the natural log of x. And then the dv has to be everything else, which is x cubed multiplied by dx. Our du is the derivative of natural log of x multiplied by dx, so 1 over x times dx. And our v is the antiderivative of x cubed, which is x to the 4th over 4. And so then we're just going to say that our integral of x cubed times natural log of x dx is equal to u times v, so natural log of x times x to the 4th over 4, minus the integral of v times du, which is x to the 4th over 4 times 1 over x. Which we have to then combine, right? So one thing I've seen that people do occasionally accidentally is they've gotten to like this stage here where they have the integral of two things multiplied together, and then they really, really, really just want to integrate each thing. But we can't do that. If we could have done that, we would have done that in the beginning and just anti-differentiated each thing to begin with. So here, we have to combine these together. We have to simplify. We get the natural log of x times x to the 4th over 4 minus the 1/4 can come out in front of the integral, and x to the 4th divided by x is x to the 3rd. And now we definitely are capable of anti-differentiating that and getting the natural log of x times x to the 4th over 4 minus 1/4 times the integral of x cubed is x to the 4th over 4. And if I was simplifying that, I'd rewrite this part as x to the 4th over 16. But we're pretending like we're not going to simplify because we're taking an exam, and we don't have to simplify. Sure. What else do I want to say about this? Oh, yeah. And then we have fun things like that. Cool. Sometimes you have to do a u sub before you do a integration by parts, which can feel kind of terrible. Well, let's look at a couple examples of that because they are things that come up. Let's look at the integral of e to the square root of x dx. Looking at this, I don't feel like I have a whole lot of knowledge. I see kind of a mixture because I've got e to the something. I've also got the square root of x, kind of there. But I don't really have things multiplied together. So with one exception, you kind of have to have things multiplied together to use integration by parts. I don't really have that, so I'm kind of stuck. When I'm stuck, here's what I do. I try u substitution, even if it feels like it's the wrong choice. So I'm going to try letting u equal the only thing that seems really valid, which is the square root of x. So u is the square root of x, and my du is 1/2 x to the negative 1/2 times dx, or if you prefer, 1/2 times the square root of x times dx. That doesn't really help me though. I don't have a 1/2 times the square root of x times dx, or even a 1/root x times dx. So the problem with this u substitution is I'm missing kind of a key ingredient. I'm missing the dx du relationship. I'm not really missing it. It's that the thing du is equal to isn't in my integral, and I don't know how to make it be in there. There's a couple ways people like to go here. I'm definitely a proponent of doing the first thing I'm going to show you, but I'll show you how you can do this other way. So if I can't make the du dx thing work, I go back to here. So we're going to go back to the beginning, and then we're going to solve for x instead. So we're going to rewrite this as u squared equal to the square root of x squared, or in other words, u squared equal to x. And now we're going to differentiate both sides. What's the derivative of u squared? 2u, and then we multiply by du. What's the derivative of x? 1 multiplied by dx. So then we can take our dx that's right there and just replace it with 2 times u times du. I will also point out, if this method is going to work, which is kind of like a u sub with a back substitution, it's the back is not really the right word there. You also can kind of get there from here if you're able to see it. So we could have, at this point here, we could have multiplied both sides by 2 root x and said 2 root x times du is equal to dx, and then replace the root x with the u it's equal to, and said 2 times u times du is equal to dx. Oh, that's the same as what we have down here. I think it's easier to do it the first way I did it, which is why I did it that way. But if you want to see it a different way, that's also fine. All right, so here's what we're going to do. And this is where we get to a point that I don't really like. We're going to rewrite this as the integral of, so first dx becomes 2 times u times du. So all of that is our dx. And then e to the square root of x becomes e to the u. Here's what I don't like what I've done. I have to use integration by parts now because I have essentially x to the first times e to the x, or u to the first times e to the u. And for some reason, it's been so hardwired into my brain, I have to use u and v when I do integration by parts. Like I mess it up if I do it any other way. And the problem here is I've already used u, and it becomes really weird to say like u equals e to the u when u is the same. So what we typically want to do, if we get to this place where we've done a u substitution already, and we know we still have to do integration by parts, is we change u. And if you are, so usually if I was doing this, I would say, well, I know what's going to happen already. I'm just going to use t instead of u. But the problem is you don't know what's going to happen already, right? You don't know you're going to do a u sub first, and then it's going to turn into integration by parts. So here's what I recommend. If you've done this and you're silly like me and can't make your u, v thing work with other letters, change your u to a w. So we're going to say that w equals the square root of x. dw is equal to 1/2 x to the negative 1/2 dw w squared 2w dw. So this is really e to the w times 2w dw. And now I can use my u and dv because they haven't been used up already. It might feel like a silly thing to you, but for whatever reason, I need to use u and v, and that's just the way it is. So now we're going to make a choice for u, just like we would have with integration by part. Well, I mean, just like we would have it is integration by parts. So we're going to pick u equal to, well, let's see, LATE. I don't have a log. I do have a power of my variable, though. I have w to the first. And I'm just going to grab the 2 along with it, because why not? So we're going to say u is 2w. And then dv is going to be the rest. It's going to be e to the w times dw. Usual process. My du is the derivative of that, multiplied by dw, because we have to use the right letter. My v is the antiderivative of e to the w, which is also e to the w. And then we're going to rewrite our integral as u times v, which is really 2w times e to the w, minus the integral of v du, which is e to the w times 2 dw. We rewrite, or I should say we finish it. We further simplify it. The integral of e to the w times 2 is just e to the w times 2, or 2 to the w. And then we finally get to go back and say, oh, but w is really the square root of x, so we can write this as 2 square root of x times e to the square root of x minus 2 e to the square root of x plus c. So sometimes you have to do a u sub and integration by parts. When that's the case, I recommend choosing a letter other than u for your u sub. Yeah, we should talk about that. Okay, so I said one thing here, and I want to make sure everyone's seeing this. So I mentioned that, what did I say? I said almost all the time, if you're doing integration by parts, you have to have 2 things multiplied together. Technically, that's always true, but you might not recognize you always have 2 things. So there's usually 1 or 2 integrals that require kind of this special other thing we do. And again, it's not really different. I'm probably making more of a big deal than I should be. Here's the example I'm talking about. The integral of the natural log of x dx. This integral does require integration by parts. And you only have one choice, really. You're going to let u equal the natural log of x. And so what does dv have to be? Yeah, dx. So technically we still have two things multiplied together. It's natural log of x times 1 dx or just dx. But it feels a little bit weird to be picking u equal to the whole integrand. But it's what we do sometimes. Very rarely. Very rarely in this class. In other classes, there are more examples that have this kind of process. This class, this is kind of the only one. There might be one other one that I'll mention in a second here. So your du is going to be 1 over x times dx. Your v is going to be the antiderivative of 1, which is x. And then we're just going to rewrite this as the integral of the natural log of x dx is equal to u times v. So x times the natural log of x minus the integral of v times du, x times 1 over x times dx. In an integration by parts problem, if you're ever letting u equal natural log of x, it's almost always going to be the case that the new integral should just simplify to some x to a power, with rare exception. That's going to be x times natural log of x minus the integral of x times 1 over x is just 1. And the integral of 1 is just x. So we get x times natural log of x minus x plus c. Hopefully your teachers have done this one in class, but in case they haven't, this is what it looks like. A similar problem, but so let me ask anybody, specifically those in Dell's class, did he ever mention the antiderivative of the inverse tangent or the arctangent? It's okay if the answer is no. He did? Oh, well, if you put it on a quiz. So this integral has the same sort of process. It's actually a little more complicated though. Yeah, I don't know if it's the best use of our time though. So I would say this is definitely integration by parts as well. You're going to let u equal the arctangent. Your dv is going to be dx. One extra fun thing about this problem is when you get to the new integral at the end, you're going to have something like the integral of x over 1 plus x squared. You have to do u substitution there. So yeah, we'll see if we have time. But I wanted to show you something else because that is not the spiciest thing you're going to see. Where did you go here? Yeah. So a number of you have seen me in office hours asking me about these terrible kinds of integrals like this one, the integral of e to the negative 2x times cosine of x dx. And this particular problem is a how do I say this the right way? There's some problems that have a very certain format that go a certain way. When you have e to the x times cosine or e to the x times sine, this next process is always what you do. So here's what we're going to do with this integration. We're going to do integration by parts twice. And then what's going to happen is the same integral is going to show back up. Let me show you what I mean. So here, again, using the late acronym, we don't have a log, we don't have a power of our variable, but we definitely do have a trigonometric function. So we're going to let u equal the trigonometric function part, cosine of x, and our dv is going to be the rest, which is e to the negative 2x times dx. Our du is going to be the derivative of cosine, which is negative sine of x, multiplied by dx. Our v is the antiderivative e to the negative 2x, which is e to the negative 2x divided by negative 2. Or if you prefer writing it as times negative 1/2, that's probably what I would actually write. So now we're going to rewrite our integral. It's going to be equal to our u times our v. So cosine of x times e to the negative 2x over negative 2 minus the integral of our v times our du. So it's e to the negative 2x over negative 2 times negative sine of x dx. I would recommend for problems like this where you feel like you're doing integration by parts more than once, simplify this before you move on. Meaning, I'm going to write this as negative 1/2 e to the negative 2x times cosine of x, just because it feels nicer to write it that way. And here, I have a minus times a minus times a minus. That's going to be minus. I also have a 1/2 I can pull out, the integral of e to the negative 2x times sine of x. Right, my negative 1 times negative 1 times negative 1 became a negative 1 out in front here, and then everything else is positive. I have a very, very similar integral to the one I started with. The only real difference is we're using cosine instead, or sine instead of cosine. And really, as far as we're concerned for integration process, like sine and cosine are practically the same function. They look they're really just each other shifted by pi over 2. So for all intents and purposes, sine and cosine are the same when it comes to integration by parts. So we're going to do integration by parts again. So one more time. This time, in fact, let me use a different color here. Sure, not that color though. So now for this one, we're again going to let u equal the trig function, sine of x in this case, and dv is going to be e to the negative 2x times dx. A word of warning. If you make the opposite choice accidentally, what will end up happening is you'll undo all the work you've done, and you'll end up getting that the integral of e to the negative 2x times cosine x is equal to the integral of e to the negative 2x times cosine of x, which is true and not at all helpful. So if you accidentally do your second integration by parts in the opposite order, you'll undo the work that was done, and the things that were there will cancel out, and you'll just have your integral left, which would feel very unsatisfying. Let's see, we need the rest of the pieces here. Our du is cosine of x dx. And our v is, again, e to the negative 2x divided by negative 2. So then rewriting the whole thing, yeah, this is equal to negative 1/2 e to the negative 2x times cosine of x minus 1/2 times all of u times v, which is negative 1/2 e to the negative 2x times sine of x, minus the integral of v times du, which is e to the negative 2x over negative 2 times cosine of x dx. And you might notice I've got something very similar to the integral I started out with. So let's write one more equation, and then we'll try to simplify this thing. So here's the whole equation. The original integral of e to the negative 2x times cosine of x dx equal to, let's see, I've got negative 1/2 e to the negative 2x times cosine of x. I've got negative 1/2 times negative 1/2, which is positive 1/4 e to the negative 2x times sine of x. And then the negative 1/2 times the negative there is going to be a positive 1/4, because it's a negative 1/2 times another negative 1/2. I said negative 3 times there, right? I did negative, negative, negative. So it should really be a negative 1/4 times the integral of e to the negative 2x times cosine of x. And look, we've essentially gotten back to the integral we started with, times whatever. And now the process is to say we're going to add that to both sides. So we're going to add 1/4 of this integral to both sides. Let's see. So we have 1 of something plus 1/4 of something, which is going to be 5/4 of that something. So we have 5/4 of the integral of e to the negative 2x times cosine of x dx equal to all of this, which feels like you should probably do less writing if you write this out. I'm doing all the writing to make sure you see all the things. And then finally, we multiply both sides by 4/5 to say that our integral of e to the negative 2x times cosine of x dx is equal to 4/5 times negative 1/2 e to the negative 2x cosine of x plus 1/4 e to the negative 2x sine of x plus c. This is the standard process for integrating something like e to the x or e to the 3x or e to the something times x times cosine or sine of something times x. It's a little bit gnarly, but not impossible. 10 minutes. Okay, sure. Something else I feel like I should mention to you. There are 3 types of integrals that require very specifically integration by parts a certain number of times. They're the following. The integral of x to some power times sine of x, or x to some power times cosine of x, or don't forget the dx, or x to some power times e to the x. And really, I'm saying x here and x here and x here. It could be a multiple of x. It could be e to the 3x or cosine of 5x or sine of negative 2x. Each of these integrals requires p iterations of integration by parts. So for example, if I said I want to find the integral of x squared times e to the negative 3x, I already know I'm going to have to do integration by parts twice. Unlike the previous problem, it's not going to be like the same integral shows up again. We have to do it. No, it's not. It's just it's a straightforward integration by parts twice. But there's a faster way to do it. So for these three integrals, instead of doing the usual process of letting u equal the thing and dv equal the thing, writing all that, there's a shortcut method that's called tabular integration. So for these three integrals, we can use what's called tabular, meaning we're just going to make a table. That's what the tabular part refers to, integration. So here's the deal. We're going to pick u equal to the usual choice here, which would be x squared. And then we're going to write all the derivatives of u until you get to 0. Derivative of x squared is 2x. Derivative of 2x is 2. Derivative of 2 is 0. By the way, this is why this only really works if you have x to a positive integer power. Because eventually, the derivative will be 0 after you do the derivative enough times. And then your dv is going to be the usual choice. We're not going to write the dx part because we don't feel like it. And then you're just going to keep anti-differentiating. So the antiderivative of e to the negative 3x is e to the negative 3x divided by negative 3. And the antiderivative of that is e to the negative 3x divided by negative 3 squared. And the antiderivative of that is e to the negative 3x times divided by negative 3 cubed. Right? Every time we're just dividing by another negative 3. And then here's the fun part. Our final answer is going to be plus this times this, minus this times this, plus this times this. And you just keep doing that until you've run out of stuff. Some other people do some weird thing where they like do some other integral thing over here. I'm not a fan of that, but it totally works if you know what you're doing. I don't really know that process works, so I don't try to do that. So then our answer is going to be, check this out, x squared times e to the negative 3x over negative 3 minus 2x times e to the negative 3x over 9 plus 2 times e to the negative 3x over negative 27 plus c. That's it. You could also do this the long way, right? You could first do u with u equal x squared, dv equal to that, do a whole process, and then you're going to get some integral of x times e to the negative 3x, and then you do it again. That's the process of tabular integration. And it always starts off with plus. So it's whatever this times this is, the plus of this times this, the minus of that times that, plus, minus, plus, minus, plus, minus, as long as it takes.
Do you think this will be fair game for like showing our work?
That is an excellent question that you know who can't answer that? Me. I do think it's a fair question. I think it's a question that you have to ask your instructor though, because they're the one who gets to decide. That said, it's still nice to see it. Because even if your instructor said, no, you can't do this, you can still write it on the side, be like, okay, well, let me check to make sure that the thing I'm getting actually works out to be that. So, yeah. I feel like there was one other thing I really had on my mind here. Oh yeah, this gnarly thing here. Yeah. So sure. Something we haven't looked at is this sort of integral, the integral of sine squared x. This is a straight trig identity, which I think, at least for those of you in Dell's class, he's giving you the identity on your exam. But we have to rewrite this as the integral of, let's see, sine squared x is going to be 1 minus cosine of 2x divided by 2. Which then I would certainly bring out the 1/2, write it as the integral of 1 minus cosine of 2x. The 1/2 sticks around. The antiderivative of 1 is x. The antiderivative of cosine of something is sine of that something. And as long as the something is a multiple of x, we're just dividing by that multiple of x. Very straightforward if we know the identity. And I think, again, for those of you in Dell's class, the identity is given. On the other hand, what if we had the integral of sine squared x times cosine of x? It's a very different problem. Right here, I would try a u sub. I see something stuck inside another function. I see sine x being stuck inside being squared. And I more importantly see that the derivative of sine is not sine. The derivative of sine is cosine, which we exactly have. So there's our u right there. There's our what? What did I underline? Du. There's our du right there. There's our u getting squared right there. So we have the integral of u squared du, which is u to the third over 3 plus c, which then becomes sine cubed of x over 3 plus c. Yeah. Throw one more thing at you. Sure. How about the integral of e to the 2x over e to the 2x plus 3e to the x plus 2 dx? Looks kind of ridiculous. It looks really ridiculous. You might think try letting u equal the denominator. That's always a good place to start. It's not going to get to the place you need to be here. Right? If you let u equal the bottom, your du is way out there. If u equals e to the 2x plus 3e to the x plus 2, your du is 2e to the 2x plus, yeah, that does not look good at all. That's not going to help me because I've only got that. And even letting u equal just e to the 2x is not going to be the right choice here because you're going to have this leftover e to the x here, which is a problem. So the idea here is to recognize this as the following. And again, I would say this is an experience interval. You have to have seen it to know what to do. It's really, really hard to know what to do with this integral until someone has been like, hey, this is how you do this integral. And that's just true some of the time. Like some of these I would never have known unless someone showed me. I would never have figured out on my own because it's just like, it's weird. So I'm going to write this as e to the x times e to the x over e to the x times e to the x plus 3e to the x plus 2. And then I'm going to let u equal e to the x. My du is going to equal e to the x times dx. So this lone e to the x over here times dx, that's going to get soaked up by the du. So that's equal to du. And then every other e to the x gets to be replaced by just u. So we have the integral of u over u times u plus 3 times u plus 2. Don't forget about writing the du. I should have written that first. And then to me, this is looking a whole lot like a partial fractions kind of problem because that denominator definitely factors as u plus 2 times u plus 1. So this is definitely partial fractions. So then you do the partial fractions, you do the partial fraction decomposition, you'd end up getting something like, what is it exactly? This ends up looking like the integral of 2. I know I'm not doing the partial fraction decomposition. I recognize that's a step we would actually need to do, but it ends up breaking down like that. Then you'd integrate both parts and get 2 times the natural log of the absolute value of u plus 2 minus 1 times the natural log of the absolute value of u plus 1 plus c. And then you have to go back and replace each u with e to the x. So this really ends up being 2 times the natural log of the absolute value of e to the x plus 2 minus the natural log of the absolute value of e to the x plus 1. See. Again, I'm well aware that we skipped the steps of doing the partial fractions, right? But that's what we had time for. All right, that's all I got. This is 2 o'clock. I have office hours. For those of you that didn't already take your test, good luck on it. For those of you that did, I hope it went well. See you all on Wednesday where we'll start talking about, I think, improper integrals. Thank you.